Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In last few lectures, we were discussing the linear discriminant functions for two category case, multi-category case, and also we have discussed the generalized linear discriminant functions. In this lecture, we are going to solve a problem on linear discriminant function for multi-category case. So this is the question. The following three decision functions are given for three class problem g1x, g2x and g3x. So these three discriminant functions are given, and here we have to sketch the decision boundary and the region of each pattern class. And the next bit is assuming that each pattern class is pairwise linearly separable from every other class by a distinct decision surface using these distinct surfaces where g12x and g13x and g23x is given. So here also we have to sketch the decision boundary and the region for each pattern classes. So in these two bit, the difference is that these two covers the two different cases to solve the multi-category classification problem. So before solving this problem, I would like to discuss some background that we have covered in the previous lectures. If remember, in last few lectures we have described the three different approaches for multi-category cases using linear discriminant function. So the first case was in the first case, each pattern class is separable from all other classes by a single decision surface. So that means we can consider C2 category cases to solve multi-category problem. Here we can denote it as in the pictorial representation as so suppose we have these three discriminant functions g1x, g2x and g3x. Okay, the decision boundary, so we can equate it to 0, and we have to find the region in which a discriminant function is greater than 0 and rest discriminant function less than 0. That means each pattern class is separable from all other classes by a single decision surface. So here in this region g2 is greater than 0 and other two discriminant function is less than 0. This region is assigned for class 2. Similarly, in this region we have g1 is less than 0, g2 is less than 0, but here g3 is greater than 0. That means this region will represent to class 3. And for this region g1 is greater than 0, g2 is less than 0, g3 is less than 0. That means this region is assigned for class 1. So here it is clear that each class is separated from the other class by using only single decision surface. So that means here W3 is separated from the other class by using only the discriminant function G3, and this is the single decision surface which separates the data point omega 3. And in this case we have ambiguous region where we cannot make any decision that whether the sample will belongs to class 1 or 2 or 3. The next case that we have discussed so in this case each pattern class is pairwise separable from every other class by a distinct decision surface. In this case no class is separable from the other by a single decision surface. Let me draw the pictorial representation of this case. So here we have three decision surface, and if you look at this decision surface, it means that we can check that which side is omega 2 and which side is omega 3. That means which is positive side and which is negative side. So if we assume that this is the positive side of the decision boundary and this is negative side, then definitely this side will be omega 2 and this side will be omega 3. Similarly, we can consider for the other decision surface as well. So if we are considering negative side is this side and this is positive side for G12X, then G1 to X will divide the samples of class omega 1 and omega 2, where the positive side will be the omega 1 samples and negative side will be the omega 2 samples. Similarly, we can define for the decision surface G13X. So now try to analyze this positive side and negative side of these decision surface. Then we can observe that this side and this side of these two decision surface are omega 2. That means these two decision surface satisfy that this region is belongs to omega 2. Okay. Similarly, this side is omega 3 because this is the negative side and this is omega 3. That means this is the region which belongs to the class omega 3, which is satisfied by the two decision boundary, that is G23 and G13. So this is omega 3. Similarly, we can define the common region for omega 1 and it will be satisfied in this region. So in this case, basically we are defining C into C minus 1 divided by 2 decision surfaces. Okay, and where we are considering that joining two class, the discriminant function is Gij equal to 0, and if x belongs to omega I, that means Gij is greater than equal to 0 for all j not equal to I. So here one thing can be noticed that in this case the omega 1 can be separated from omega 2 by g 1 to x equal to 0 and from omega 3 by g13 x equal to 0. So it is very clear here that each pattern class is pairwise separable from every other class by a distinct decision surface, which is very clear from this statement. And in this case we have ambiguous region here, and we have the third case try to understand this case using a pictorial representation. So here we have three decision surfaces. This is g1x minus g2x equal to 0. This is g1x minus g3x equal to 0. This is g2x minus g3x equal to 0. So here we can define that this region is omega 2, this region is and this region is omega 1. So you can notice here that here we don't have any ambiguous region. Therefore, in this case there are C decision surfaces and gkx, that means kth discriminant function, will be defined using this expression where k is equal to 1 to c, and where c is the number of class and x sample will belongs to omega I if gix is greater than gjx for all j not equal to I. So here I try to illustrate these three cases in more detail. Now we can solve our problem. So look at the first bit, that we need to sketch the decision boundary and the region for each pattern class. So here it is not mentioned that this is case 1 or 2 or 3, but from here we can conclude that each pattern class is separable from all other classes by a single decision surface. So this is basically the case 1. So now we can solve the first bit using the case 1. So we have given in the first bit we need to sketch the decision boundary and the region for each pattern class, where it is assumed that each pattern class is separable from all other classes by a single decision surface. So first let us draw these three decision boundaries, so we can make the points which will help us to draw the decision boundary. Okay, so let us draw these three straight lines on the graph. Now draw this straight line g2x. Here x1 is 0 and x2 equal to 5. So here we have one point, and other point is x1 equal to 4. So here we have another point. Similarly, we can draw the decision surface G3. So here we have the 2 points that we have calculated. So x1 equal to 4. So this is 4 and x3 equal to minus 3. So this is one point, and the another point is x1 equal to 0 and x2 equal to minus 5, and this is x1 0 and here it is minus 5. So now we have to join these 2 points. So this is g3x, g2x. Then we have to mark that which side is positive, which side is negative. Just consider g1x. So here we have the origin. Okay, so in g1x we will put the value x1 equal to 0 and x2 equal to 0. So that is the basically origin. So when we put g1x equal to 10 into 0 minus 0 minus 10, which is minus 10, which is less than 0. So that means, so this side is negative and this side is positive. Similarly, we can compute for g2x. So just put the value, so just try to put the origin in g2x. So g2x equal to 0 plus 2 into 0 minus 10. So this is minus 10, which is less than 0. That means the origin side of g2x will be negative and the other side will be positive. Similarly, for g3x also we can compute. We will obtain that origin side is negative and other side is positive. Now we have to find that in which region g1x is greater than 0 and other g2x and g3x are less than 0. Now scan the individual regions. So here g1x is greater than 0, g2x is less than 0 because this is in this region, and g3x is also less than 0. So here it satisfies that this is our omega 1. So we can say that this region belongs to the class omega 1. Similarly, try to scan this region and you will find that in this region we have g1x is less than 0, g2x is less than 0 and g3x is greater than 0. So that means this region will be represented as the region for class omega 3. If you will scan this region, then just you notice here that g1x is greater than 0, g2x is also, and g2x is less than 0 and g3x is greater than 0. So here we have the two values are greater than 0. So this is ambiguous decision. So we can say that this is ambiguous region. Similarly, all the regions we can scan and we can find that this region is g1x less than 0, g2x is greater than 0, g3x is less than 0, so where it belongs to the omega 2, and rest of the regions are ambiguous region. These are ambiguous regions. This is also ambiguous region where we cannot make the decision whether the sample will belongs to class 1, 2 or class 3. So here in this problem we have drawn the decision surface G1x, G2x and G3x, and also we have shaded the region of the different classes. Now move to the second bit of this problem. In second bit, we have assumed that each pattern class is pairwise linearly separable from every other class by a distinct decision surface, and we assume that g1 to x is g1x equal to 10 x1 minus x2 minus 10 equal to 0. g13x equal to g2x equal to x1 plus 2x2 minus 10 equal to 0, and g23x equal to g3x equal to x1 minus 2x2 minus 10. So whatever the parameters are given, then you can conclude that this is the case 2. Okay, so here we have the same decision surface, but now we have the different case, so we can draw the same straight lines as we have drawn in the first bit. So this is the origin, this is x1 and x2, and we can draw the points. This is the first point, 1, 0, and another point is 1.55. This is g1 to x equal to 0. Other line we have x0 and x2 equal to 5. And x1 equal to 4, x2 equal to 3. So the line joining these 2 points, this is g13 x equal to 0. The third line, x1 equal to 4 and x2 equal to minus 3, and x1 equal to 0 and x2 equal to minus 5, and this is g23x equal to 0. Now we have to define the positive side and the negative side of the decision surfaces. So first we can look at g23x equal to 0. So here in this equation we can check that origin is in which side, in negative side or positive side. So just put the value of x1 as 0 and x2 equal to 0, then we can find that for x1 equal to 0 and x2 equal to 0, which is the origin for this g23x is less than 0. That means the origin is in the negative side, and the same thing holds for all the decision surfaces. That means origin is in the negative side. So we can mark the positive and negative side. So the positive side is omega 2 and the negative side is omega 3, because the first term is 2 and then 3. So positive side is omega 2 and the negative side is omega 3. Similarly, for G13x, this is negative side and this is positive side. So negative side is omega 3 and positive side is omega 1. And for G1 2x, this is negative side because in the left hand side we have the origin and this is positive side. So negative side is omega 2 and positive side is omega 1. Now we have to look at the common region where the two decision surfaces satisfy for a single class. Now this decision surface satisfy for omega 1 and this decision surface satisfy for the same class omega 1. It means this is the omega 1 class region and this region is omega 2 by G1x and this region is omega 2. So here this is the omega 2 which is defined by these two decision surfaces. And for omega 3 we can define, if you look at these, this side we have omega 3 and this side we have omega 3. That means the complete region is omega 3. So here we have defined omega 1, omega 2 and omega 3, which is defined by the shaded region. So here we have drawn the decision surfaces and the region for different classes. I hope I am clear to you. If you have any doubt, you can ask in the comment section. Thank you.